Okay. In this video, we're going to look at how to assign the structure from having multiple forms of spectral data available. What I'm going to talk about here is considered generally the most logical way to approach it, but if something works different for you, go with it, okay? The only objective here is to come up with a unique structure that fits all of the spectral data given. Okay, so we're given an unknown compound. Our task number one should be to establish the molecular weight and the formula. Okay? All right, the most useful tool here is the mass spectrum. Okay? Looking at the paranion corresponds to the molecular weight, and we can look at the isotope patterns, the M+2 peaks in most cases, to see if we might have other elements present like chlorine or bromine. Okay? All right. Other places give us some idea of the formula too. For example, the proton NMR. If we look at the integration numbers underneath each of the peaks, okay, they ought to add up to the total number of hydrogens in the molecule. If the integration values add up to 8, that means that there's likely 8 protons, but there could be 16, 24, any sort of multiple of 8, depending on the symmetry. Okay, C13 NMR can give us an idea of the maximum number of carbons. Counting the number of signals gives the minimum number of carbons in your compounds. There might be more because of symmetry, okay, but this gives us at least the minimum number of carbons in the molecule. Okay. Once the formula is established, there's a very important piece of information that can be gathered simply from the formula. And that's how many rings and double bonds are present in the molecule. Sometimes this is called the sum of rings plus multiple bonds. That's SODAR. Index of hydrogen deficiency or degrees of unsaturation. These are all synonyms for the same thing, and they come directly from the molecular formula. This arises from the fact that an alkane has the formula CN H2N plus 2, and this ends up being the maximum number of hydrogens per carbon. And anything less than that implies that we have either a ring or a double bond present. Okay, so this is the formula here that you would use if you had a hydrocarbon. Okay, the sum of the rings plus double bonds is equal to the number of carbons times 2, add 2, that gives us this alkane number up here. Then we're going to subtract the number of hydrogens that are actually in the formula and divide it by 2. Okay? When you're doing this, what do you do with elements that are not carbon and hydrogen? Well, you're going to pretend that every halogen is just taking a site where a hydrogen would be, so you're going to pretend that every halogen is a hydrogen. Okay? You drop oxygen and sulfur from the formula, and when you have a nitrogen present, you subtract one nitrogen and one hydrogen from the formula. Right? So if we look at this compound C6H11ClO, this means that we would drop the oxygen and we would pretend that the chlorine is just another hydrogen. So we would be looking at it as if it's C6H12. All right? And when we look at our formula, or when we apply this formula now to C6H12, we see that this formula that we started with, C6H11ClO, is going to have one ring or one double bond in it. Okay, let's look at this more complex formula. What do we do here? We're going to pretend the oxygens aren't there. And pretend that the bromine is actually a hydrogen, so there's 4 hydrogens, no bromines in our pretend molecule. Okay, and for each nitrogen, we're going to subtract one nitrogen and one hydrogen from the formula. So we're going to take C7H4, that's our pretend molecule, N2, and we're going to still have C7, but for each nitrogen we're going to subtract a hydrogen. So it's going to look as if it's C7H12. That's the hydrocarbon equivalent to something of this unsaturation level. Okay? All right, so rings plus double multiple bonds here goes into this formula here. 7 times 2 is 14. Add 2 is 16. Minus 2 goes back to 14. Divide by 2 is 7. Okay, what do you do if you work this formula and you get an odd number? All right, you want to go back and work it again because you've made some sort of mistake, or it's a rare compound that's a stable free radical. That's the only thing I can tell you. When you work this formula, you should get a even number up here, and it should divide to be a whole number. Okay, so if you get a half or something like that, something is probably wrong. All right, so we're going to use now, after we've done this, we're going to use the NMR and the infrared to help ascertain whether the unsaturations are rings or double bonds. So we see that it's easier to find double bonds or triple bonds than rings. We see that double bonds have unique chemical shifts in their proton and C13 spectra, and we see that carbon-oxygen double bonds also have unique C13 and infrared spectra. Okay. Task number 3, we're going to identify all the functional groups present that we possibly can. For oxygen and nitrogen containing functional groups, the infrared is probably our best source because they don't have an NMR. But for a functional group where a hydrogen or a carbon is involved, the infrared and the C13 the infrared and the proton or C13 NMR might also be helpful. Okay, our last task is we're going to identify the chains using proton NMR and assemble the molecule. Proton NMR is our key because of the rule of coupling. It's the only thing that we have covered that transmits information across a carbon like this. Okay, so this is going to be key to nailing the final structure. Okay, so this is actually just an exercise in working a puzzle. We're going to use the information as a puzzle, and periodically it's going to be a good idea to do an inventory. How much have we found, so we know how much farther we have to go. Okay? All right, so the rest of this is just a few sample problems. Assign a unique structure that has the formula C5H9ClO2 and fits the NMR and IR data. All right, we don't have to figure out the formula. It's given. And this is an important point. No matter what structure you come up with, it should be C5H9ClO2 because there's no arguing with that. Okay? All right, what else can we say about this? Okay, unsaturation. How much unsaturation is present? Okay, we're going to pretend that this is C5H10, and that's going to have 1 degree of unsaturation. All right, can we find that degree of unsaturation? Yes, we can. It's a C double bond O. There's good evidence there, right, in the infrared. There's a C double bond O stretch. There's another indication of a C double bond O right there in the C13 NMR, that unique peak right there. All right, we have a couple of sp3 carbons that might have a chlorine or an oxygen on them right here. Okay, they have kind of a highish chemical shift. Okay, so let's see if we can assemble this molecule. All right, so let's look at a few things here. We kind of are looking at the individual pieces. And what you see here is we have 3 hydrogens for one signal. This almost always involves a methyl group. So for this methyl group, we can see that it's a methyl group. And because of the fact that it's a triplet, that means that right beside of it, it has to be a CH2. Okay? Here's another methyl group. It's a doublet. Right beside it, it must mean that we have a CH. Okay? All right, so let's look at the inventory here. We have we found this carbon and 2 ethyl groups. So what have we found here so far? We found CO, C2H5, and C2H4. All right, if we had this together, C5, H9, and an oxygen. All right, we've identified every hydrogen in this molecule and every carbon. We just need to assemble these pieces. So we have an ethyl group. That means there's one site right here. Okay, we need to have we need to find a place for one more oxygen and one chlorine. Okay. All right. So CH3 is beside CH2. This is going to give us a quartet. This quartet here integrates for 2. So therefore this is the CH2. It has a chemical shift of 4.2. That means it needs to have an oxygen or a chlorine right there. It can't be a chlorine because the molecule would end right there. It couldn't go any further. It would just be chloroethane. So it must be the oxygen right there. All right, we have to have CH3, CH2O. Okay, if we look at this one, this is the quartet here, okay? This is our peak at 4.4. All right, we still need to find the chlorine. So this is really the only other place to put it. Now, where does the C double bond O go? Okay, so remember that the ketone is actually going to have a couple of other sites right here. So our structure has to be this compound right here. Ethyl alpha chloropropionate would be the name for this compound. Okay, so this is our structure right here. Okay, again, for each of these, I think you should pause it periodically just to make sure you can try and do it on your own. All right, let's look at another one. Here we do not have the formula. We've got the molecular ion. It's at 178. And we have this hint here that there's no significant M+2 peak, so it probably doesn't have any chlorine or bromine in it. Okay, we're also given some other information that the compound is ultraviolet active. All right, so we have to establish the formula. What we typically do here is we start out with the nearest hydrocarbon formula. Okay, and most people maybe have forgotten their multiplication tables by 12, but the place we're going to start here is with C13, H22. We could start with C12, but then we need a ridiculously high number of hydrogens. That's more than that number of carbons can handle. So C12, H34 isn't really a good starting point. Potential, but that's not the best place to start here. We could have more carbon, C14H10, but this would just be a molecule that's incredibly unsaturated. All right. Okay, so let's start there. Okay, and what you see here is that one thing we can do to keep the molecular weight the same is consider dropping 4 hydrogens for every oxygen that we had. Okay, so if we start with C13H22 and continue doing that process, we'll keep the molecular weight the same. So all of these are going to have the molecular weight 178. Okay, if we look at the number of peaks, there's 1, 2, 3, 4, 5, 6, 7, 8. So there's at least 8 carbons in our molecule. There might be more if there's some symmetry. If we take these integration numbers, 2, 4, 5, 8, and 6, that's 14. All right, this looks to be our most reasonable formula. Okay, all right, so how unsaturated is that formula? C11H14O2 has 5 rings plus double bonds. Remember, when we have a really high unsaturation count, what we typically consider is that it's very likely that we have an aromatic ring. And this is because an aromatic ring gives us a lot of unsaturation in a small area. Okay, so benzene itself has 4 degrees of unsaturation, a ring and 3 alkene groups. That's far more reasonable than having a molecule with 4 different alkene groups in it. All right, there's some things that verify that we have an aromatic ring as well, right? And that's this these peaks right here. Okay, these are hydrogens and a benzene ring. Okay, all right, so we have 5 degrees of unsaturation. If we have a benzene ring, that would give us 4 of them. We have one more unsaturation that's not covered by the benzene ring, and right away we can see what it is. Again, it's in the infrared spectrum. That's the C double bond O right here, and right here is also a peak that's consistent with a C double bond O. Okay, so this looks like to be a compound with a benzene ring and a C double bond O in it. All right, how substituted is the benzene ring? Benzene itself has C6H6. All right, so if we have less than 6 aromatic hydrogens, that tells us that we have a substituted benzene ring. If we add up our integration numbers down here, 2 and 2, that's 4. Therefore, this is a disubstituted aromatic. Okay? All right. It can have as many as 6, but it's only got 4 aromatic hydrogens. Therefore, there must be 2 things on the benzene ring. Okay, let's now consider what else we can find in this molecule. Here we have a doublet, 6 hydrogens. Okay, we've seen that pattern in the NMR section of this chapter, right? And that's almost always an isopropyl group of some sort. Okay, and you see that not only do you have the doublet of 6 hydrogens, but here we have this hydrogen that's heavily split by 2 different methyl groups. So here we have a septet. You're saying, I only see 5 lines. Well, remember, in the discussion back then, we said it's often difficult to see the outer lines. Okay, they're here. They're puny little pimple-like structures that you can just barely see, but they're there. Like I say, counting, like I said previously, counting the number of lines in a heavily split pattern isn't always the best way to go. All right, so there's an isopropyl group in this molecule. There's a C double bond O. There's a disubstituted benzene. Okay? This is a CH3. Right? So we've accounted for every hydrogen and every carbon in this molecule. We still have one more oxygen that we haven't looked at, right? One of the oxygens is in the C double bond O, but there's another oxygen present. Okay, so what do we have for as the final structure of this molecule? So we have a benzene ring. It's got two things on it. All right. Notice in the C13 NMR that we don't have enough peaks. This tells us that we have symmetry. Okay, and the most symmetrical pattern for a disubstituted benzene ring is para, right? So we more than likely have a para-substituted benzene ring. Let's look at our chemical shifts. This chemical shift of the methyl group is 2.5. This is only consistent with our methyl group being adjacent to a C double bond O, or adjacent to, or actually directly on a benzene ring. Okay, so that's what type of methyl we have here. This septet here suggests that there is not an oxygen here. Okay, this chemical shift of 2.8 or so isn't high enough to support there being an oxygen here. If this was an oxygen, this chemical shift would probably be way above 4. Okay, all right, so there are a variety of structures we can propose. This is the one that we actually have. Oops, sorry. CH3 this is our structure right here. Okay, I think I'll just advance it. Sorry, I wrote over it. Sorry about that. Let me write it in a better place. All right, so this is the correct structure. Let me just add one other thing before we move on here. There's another structure that, based on what I've talked about so far, I have to give full credit for this alternate answer right here. Okay, sorry, oxygen there. Okay, and this illustrates something I said previously, that when we get to the actual chapters that deal with different types of C double bond O's, we'll be able to distinguish these two structures. An ester would look a little bit different from a ketone. Okay, actually neither of these are a ketone, but we would be able to easily distinguish these two compounds. Actually, no. When I think about it, I think this is just as good a structure as the other one. Okay, all right, so these two structures would fit. This is the actual structure, but this alternate structure here, I can't see any reason why I should not count that. I should not give that full credit. Okay, there are more sophisticated ways to tell those two apart. Okay, here's the last one. This one we have a formula, so we don't need to estimate what the formula is. It's 5 rings plus multiple bonds in this molecule, we're going to suspect that there's a benzene ring. Okay. A lot of evidence that there's a benzene ring here, particularly these peaks right here. Okay. All right, there's a lot of symmetry to this molecule, right? It has 11 carbons, but only 1, 2, 3, 4, 5, only 7 peaks. Only 7 signals. So this is a molecule that's going to have an appreciable degree of symmetry. All right, if we look at the aromatics, there's only four hydrogens present, so therefore it's disubstituted. Excuse me. Okay, what else can we say here? All right, what's our other aromatic, or what's our other unsaturation? Here we see the most unique peak of all, and that is the peak for an aldehyde. This is the only type of proton that comes at 9.7. If you're given an unknown of this type and the person asking you the question gives you an aldehyde, you really should say thank you, okay? Because it's the most unique type of signal there is, okay? All right, we see a lot of symmetry again in the aromatic ring system here. We see 2 doublets, okay? And this is consistent again with the para disubstituted system. Okay. All right. Our aldehyde isn't going to have any coupling, so let's just put it right here. All right. So we have the structure. What is this? This is C7H5O, and if we look at our original formula, C11H15O, and subtract this, we have 4 carbons that we haven't accounted for, 10 hydrogens, and 1 nitrogen. Okay, so what is the rest of the molecule here? We see a triplet for 6 hydrogens and a quartet for 4 hydrogens. A triplet and a quartet we've probably come to associate with an ethyl group. But an ethyl group is 3 and 2. This is 6 and 4. So this is 2 ethyl groups, right? That's the only way we can get such a symmetrical pattern out of so many carbons and hydrogens, okay? All right, so our actual molecule is going to have a nitrogen here with 2 ethyl groups on it, okay? And this is the compound that is this unknown right here. All right, so there are 9.7 parts per million. Yeah, an aldehyde. Fewer carbon symmetrical, benzene rings present. Benzene rings disubstituted. The rest of the proton NMR looks like 2 equivalent ethyl groups. And this is our molecule. Okay? And this is the last of the spectroscopy chapter. I think that what you've seen in these last few slides is that spectroscopy is fun. It's like working a crossword puzzle. Even if you don't want to do it, you might want to do it just for fun. Okay? It's a kind of a very intellectually gratifying exercise is these combined structure problems. If you do a few of them for practice, you actually get quite good at it. You can do them quickly. And that's the key to success in this chapter, is to get as much familiarity as you can with structural assignment. Okay? All right, so this will end the spectroscopy video. That's just for my own undergraduate class, so that's not really relevant there. So I'm going to end this video right here.